Good morning, everyone. Welcome to Chemistry with Professor John. Okay, we are looking at nucleophilic substitution and eliminations. And if you look at the textbook by John McMurray, it's chapter 11. All right. Now, this is a quick review and some homework problems. Okay, substitution is very simple. Pretty much you replacing the X, which is known as a leaving group. Rx is known as substrate. X is a leaving group. Nucleophile, Nu is for nucleophile. It could be a molecule or an ion that's electron rich. Okay. Now leaving group, either halogens or tosyl. Okay, that's OTS. It could be water or alcohol like methanol. Okay, so incoming nucleophile. This is a nucleophile. Come in, bonded to the methyl. Okay, and replacing the Br. So we got a new molecules. Now, like I said, anything with electron, acetylide or the alkynium ion is also electron rich, and that come in replacing the Br. Okay. In terms of stereochemistry, okay, in terms of stereochemistry, all right. In terms of here we go. In terms of stereochemistry, if we start out with R for SN2 reaction, we start out with R. Okay, so you can think about that as a right-handed Br. Now the incoming nucleophile Cn minus cannot come on the same side because Br is has a lot of a few 3 electron pairs, so that's take up space, and it would not let the Cn minus come in from the same side. That's a no-no. It has come in from the back side, okay, pushing the hydrogen to the other side. You guys can see that. So that become left-handed or S. We can think about it that way. You guys see? So it's always inversions. So if you have the O TOS on in front of you, the replacement group will be in the back of you, away from you. Okay. If there's no stereochemistry, you don't have to worry about it. Okay. Now, in terms of reactivity, think about it as a rate. The primary is the best. Okay. The methyl is the 0 degree. Okay. Primary because it's got one branch. The carbon right here has one branch. Secondary because this carbon right here has 2 branches. Okay. So in a tertiary, forget it. Right. The rate is almost not no reaction there. So primary or methyl would be the best. In terms of solvent, protic solvents are not good. any polar solvent that's not protic, meaning it doesn't have any acidic hydrogens. Okay. Any other solvents are good. Polar solvents are good. So you got this coming in here. This carbon is not chiral, so you don't have to worry about it. And Br takes off. If you run the reaction at the double bond carbon, sp2, there'll be no reactions. Okay. So there's a few factors affecting the SN2 reactions. That's the strength of the nucleophile, the incoming group, the bulkiness of the nucleophile. That's a steric factor. Okay, the nucleophile, if it's bulky, it's not good. Okay, so if you have something like this, not a good nucleophile. It's a good base though. Because of the negative, okay? Can take the hydrogens, okay? All right, so that's SN2, and then SN1, you can see it's exactly the opposite. Tertiary is the best for SN1. The reason why, because it's formed the cation. So when you do SN1, right, you don't notice that there's water ethanol, no strong nucleophile. Okay, so very likely it's going to be SN1, and you have 60% inversions, 40% retention, so almost 50-50. Okay, how come, right? So look at a tertiary. After Br leave, you got a tertiary cation, which is good, okay? Tertiary cation is flat. Well, this molecule is not polar anyway. I mean, it's not chiral. And then so you got water coming in, either from the top or bottom. It doesn't matter because there's no chirality here. Water comes in, another water molecule take away the hydrogen, so we got a neutral alcohol. So for SN1, tertiary is the best because it forms the most stable cation. All right. Now, this is the cation. So think about, this is a secondary, okay? That's sp2, it's not good. Well, this is the secondary, but also allylic. Allylic means next to the double bond. That's a primary, okay? So this one should be the best because when you form the cation, not only a secondary, but we can also do a resonance. You can see it, okay? So resonances. And then this one is the second best. and then the primary, and then the double bond, because double bond, the sp2 bond is too strong to break the bromine. Solvents, anything to work. Water is best because it's polar, but any polar solvent will do a good job. Okay, here's the couple example. Now, Levendrup, we got a nucleophile right there, we got solvent. Okay, now that's not a strong nucleophile, so that's moderate actually nucleophile. Now, remember this one is a secondary and it's also next to double bond, so it's allylic, right? So this one is pretty difficult to call, but it's gonna form a stable cation. I'm talking about cation that can do resonances. There, so you can do resonances. There you go. So it's pretty good. That's gonna come out first, and then you have CH3COO minus coming in. That's the same as OAC. Okay, abbreviate as OAC. That's acetate. Okay, on this one it's primary, so, and that's a strong nucleophile. So obviously it's gonna be SN2 for this one. Okay, more example. How about this, right? And this is a good one. Also allylic, you notice that next to double bond. So that oxygen will pick up the hydrogens to become there, and now it's a very good Levendrup. And when it leaves, it forms the cation, and that's a secondary allylic. So it's pretty good, and then the Cl minus comes in, and to give us the product. So obviously this is the forming the cation that tells us that is SN1. As long as form the cation, it's got to be unimolecular. Okay, same for this one. This one right here is allylic. So, but that's a strong nucleophile though, okay? That's like OCH3. Strong nucleophile tell us that it's gotta be, and that carbon right there is still sp3, because that's a CH2 with 2 other bonds. That's 4 bonds. So that's strong nucleophile. We're gonna go for SN2. It looks very tempting for SN1, right? All right, here we have substitutions reactions. So those are substitution. Sorry, here we have elimination reactions. Now, substitution give us the substituted products. Elimination eliminate Br and also eliminate hydrogen somewhere. Okay. So it's different. Instead of substituting, it's eliminating. So it's form a double bond. Sajap rule said that if we form the internal alkene is more stable. It's a double bond surrounded by branches. Okay, the terminal one is not as stable, like no branches over here. Right, so it's not as stable. So that's your major product will be 2-butene instead of 1-butene. That's internal alkene. Now, same for this one. Eliminations. So it's formed that instead of, this is the major product instead of outside. That's internal. Okay, so how does it go? E1 form the cation, just like SN1. The leaving loop take off, form the cation. So instead of B coming in here, no, it take the hydrogens, okay? Take the hydrogens and form the alkene. Notice for the E2 mechanism, there's no cation formations. You can see 3-step happen at the same time. The base come in, wrap the hydrogens, and then form the double bond, and then X, which is the leaving loop, takes off. So you get a nice alkene. E1 conjugate base. The only difference is the hydrogen got taken off first instead of forming the cation. It's forming the anion, and that's what we call conjugate base. Okay. And the anion form the double bond and kick out the leaving loop and leave us alkene. Okay, predict. Here's an exercise for you. Predict the major products, major and minor product for the following reactions. Well, first of all, it's good to know what degree that is. Okay. That look like it's tertiary. Okay, if it's a tertiary, but we got a strong base, a strong nucleophile, that's strong. That K plus. OH minus is pretty strong nucleophile, strong base. Right? So it's got to be substitution or eliminations because it's strong. But because it's a tertiary, no SN2. So that's why that put us on the E2 eliminations. And we got 2 different products. The more substituted one is the major product than the terminal one because it's just more stable. Okay, we got more example. You guys can give it a try, and then definitely we'll discuss that in the next video. I also put the green chemistry concept here. Okay, from the textbook, which is pretty good. All right, so we'll go over this together in the next video, everyone. Well, thank you for watching substitution and elimination reactions in organic chemistry.